Every year, a hidden machine awakens in silence, just as holiday lights begin to glow across continents. It's not a single machine, but an immense, synchronized system. Fleets of refrigerated trucks, sensor-filled containers, port cranes, customs terminals, and digital control towers, all tuned like instruments in a mechanical orchestra. Their shared mission: to move 4.2 million tons of meat across borders in less than 2 months. In this narrow window, the logistics of global protein accelerate to the edge of feasibility. The rhythm tightens, the tolerance for error vanishes, and any delay, any failure in this choreography ripples through the entire supply chain like a discordant note in a symphony. During the peak holiday season, a span of just 45 days, the stress placed on global cold chains equals an entire year of demand compressed into a single breath. Border crossings, already strained under routine conditions, become critical bottlenecks. A 1-hour delay under sunlit tarmac can compromise 200 tons of chilled beef, not from heat alone, but from the subtle collapse of internal airflow balance, from invisible temperature gradients accumulating at pallet cores, from sensors that lose sync with what they're supposed to protect. It's not dramatic, it's systemic. And in the world of meat logistics, system failure doesn't announce itself with noise. It whispers in bacterial counts, surface dehydration, color loss, and claims of rejected cargo. There's a common belief that moving meat is simply a matter of keeping it cold. But refrigeration, while vital, is only one component in a system far more complex. What's actually in motion is a high-precision choreography of thermal inertia, atmospheric control, load dynamics, customs documentation algorithms, microbiological time windows, and energy flows. It's a chain in constant modulation, adjusting to ambient conditions, cargo density, journey length, and the physiology of the product itself. Each variable demands real-time recalibration. Refrigeration without airflow management creates cold shadows. Container routing without customs, pre-clearance generates temporal gaps. Each part affects the whole. To understand the scale, imagine a naval propulsion system, a ship whose engine must sustain constant velocity across changing tides and underwater resistance. Like that system, meat logistics demands constant adaptation. Instead of propellers and fuel, we're dealing with airflow velocity, digital pre-cooling synchronization, and microbial stability. And instead of waves and ballast, we confront border queues, desert heat, and tropical humidity. In both systems, there's one goal: uninterrupted propulsion. Meat in transit must never stall, it must never overheat, and it must arrive structurally intact, biologically stable, and economically viable. But during the holiday rush, even small misalignments multiply across the chain. A cooling chamber assigned with incorrect airflow speed may not be noticed at the terminal, but during transit, it creates condensation zones, microscopic at first, that turn into bacterial vectors. Multiply that across dozens of loads and thousands of kilometers, and what seems like a configuration oversight becomes a systemic loss, invisible until it's too late. This is how a minor programming error, unnoticed during dispatch, ends up in claims, recalls, and destroyed shipments. To truly grasp the complexity, think of the cold chain not as a straight line, but as a kind of mechanical intestine, a duct of gears, sensors, valves, and pressurized corridors. Through this duct, perishable proteins are propelled like living tissue, across climate zones, through temperature differentials, over bureaucratic hurdles, under the gaze of customs and quality inspectors. The journey never stops. If it does, even briefly, the chain ruptures. And unlike metal or plastic components, meat cannot be reconditioned. It either arrives on time, within thresholds, or it doesn't arrive at all. In this invisible system, time is not a neutral backdrop. It's a material. It shapes quality. It erodes value. And in the global choreography of meat logistics, time must be engineered with the same care as temperature, speed, and volume. What you'll see next is not just how meat is transported, it's how time is captured, channeled and controlled by machines, people, and decisions that most never see. The journey of meat doesn't begin at the border. It begins in the final kilometer of the farm road and continues through the chaotic orchestration of docks, terminals, and loading zones, each segment carrying risks that rarely appear in textbooks. Surprisingly, the most vulnerable sections of the entire journey are not the vast highways or international air routes. They are the first and last 100 kilometers. It's during these short spans, where refrigerated trucks navigate rural heat or idle near urban ports, that most failures occur. Delays in docking, uneven terrain, solar radiation during loading, and human error in temperature setup all act as silent saboteurs. The damage rarely announces itself immediately. It unfolds gradually, molecule by molecule, across a chain designed to never pause. Inside each refrigerated container, meat is not simply stored. It's suspended in a delicately controlled thermal environment. And one of the most misunderstood variables in this system is thermal inertia. Pallets filled with dense, moisture-rich cuts of meat resist temperature change, for better or worse. Logistics managers often rely on container set points, the programmed internal temperature, as if that alone were enough. But the real challenge lies in directing airflow, not just cooling. Without proper airflow geometry, cold air fails to reach thermal shadows, those internal regions where heat lingers due to insulation inconsistencies or poor stacking patterns. As a result, surface-level freshness becomes a misleading metric. Beneath, degradation has already begun. To counteract this, modern container technology now borrows from another demanding industry: mining. In ore refrigeration tunnels, engineers must cool massive volumes of mineral with precise airflow modulation. This technology, variable speed compressor systems, has made its way into meat logistics. These compressors adapt in real time to the thermal mass of each load, regulating airflow speed and pressure with surgical precision. Instead of simply cooling a space, they sculpt air currents through meat stacks, minimizing dehydration and reducing bacterial risk. The result is not just fresher meat, but a more predictable journey, one where internal container conditions remain stable, even as outside temperatures fluctuate wildly. But technology alone doesn't guarantee protection. In 2022, a meat cooperative in Brazil faced a brutal lesson in systems design. During a holiday export surge, containers were loaded without recalibrating airflow paths. Cuts of beef, densely packed to maximize space, restricted cold air movement. Within hours, internal condensation began to form. It wasn't visible from outside. It wasn't detectable through basic temperature checks. But within 24 hours, the microclimate inside the load shifted. Bacterial colonies multiplied, exceeding legal thresholds. The entire batch, valued at over $12 million, was rejected at destination. The data showed no equipment failure. The problem had begun in the programming, long before departure. To visualize this hidden dynamic, think of a refrigerated container not as a box, but as a mobile cold reactor. Inside, air behaves like a fluid under compression, not just moving randomly, but shaped and directed like hydraulic oil inside a piston engine. The design must guide this fluid into every corner, every crevice, with enough force to overcome the load's resistance. If airflow fails to penetrate these zones, they become thermal dead spots, invisible gaps where the cold never arrives. And when that happens, the container does not transport meat, it transports loss. In these convoys of refrigerated trucks, often moving across mountains, deserts, and ports, what appears to be a stable operation is, in fact, a high-precision thermal experiment in motion. Every kilogram of meat carries not just nutritional value, but a fragile equilibrium. Preserving that equilibrium, kilometer after kilometer, requires more than cold air. It requires engineered airflow, informed configuration, and constant adaptation. Because in this system, a deviation of just 0.8 degrees Celsius is not a technicality. It's a decision worth millions. Before we move on, here's something worth your attention. Take a second to check the pinned comment. There's something there that speaks directly to those who appreciate how complexity can be turned into efficiency. A refrigerated truck can travel thousands of kilometers without failure. Its sensors can maintain temperature with decimal precision. Its compressors can modulate airflow with algorithmic accuracy. But all of that precision collapses the moment the vehicle is forced to stop, especially at a border. Customs zones are the blind spots of global cold chains. They are transitional spaces where infrastructure loses control, where perishable cargo enters a waiting state, and where refrigeration alone is no longer enough to protect what's inside. A perfectly chilled truck, parked for hours under sun-exposed asphalt, becomes a greenhouse in disguise. This happens not just because of ambient heat. It happens because of a subtle, often ignored phenomenon: residual respiration. Meat, especially high-protein cuts recently chilled, continues to emit metabolic heat for hours. This heat, trapped within the load, begins to raise internal temperatures from the core outward. From the outside, the refrigeration unit may show stable values, but inside the pallets, a different process unfolds. Latent heat combines with solar reflection and container wall conduction, forming a microclimate that slowly undermines freshness. Ventilation systems, if passive or poorly designed, cannot disperse this load-generated heat in time. What few operators realize is that cold preservation is not a static condition. It's a respiratory balance. And within that balance, two often overlooked details play a decisive role: ventilation geometry and door seal memory. The geometry defines how air circulates inside the container, whether it flows freely or stagnates in corners. The seal memory refers to how container doors deform over time and after repeated use, potentially creating invisible entry points for warm air and moisture. Together, these two elements determine whether condensation will form, whether bacteria will gain a foothold, and whether meat will survive the crossing with its structural quality intact. In the Netherlands, a high-throughput logistics terminal redefined how border zones interact with refrigerated cargo. Instead of focusing on refrigeration capacity, they redesigned the customs interface itself. Dynamic insulation curtains reduced heat infiltration. Oxygen depletion systems suppressed microbial activity during inspections. The result wasn't just a marginal improvement. It was a 42% reduction in spoilage claims on imported meat. And notably, it was achieved without increasing refrigeration power. It was a matter of architectural intelligence, not brute force. The challenge is simple to describe but hard to visualize. Meat must keep breathing, not literally, but thermodynamically. The cold chain is not just a line of machines. It's a simulated lung. It must circulate, exchange, and protect internal atmospheres, even when the truck isn't moving. When the container is paused for inspection and ventilation is suspended, the system suffocates itself. Heat accumulates. Moisture condenses. Proteins begin to break down. And by the time the vehicle is cleared to move, the damage has already occurred. Imagine moving a lung through a desert. You can shield it. You can insulate it. But unless it continues to breathe, the tissue will collapse under its own weight. That is the paradox of customs zones in meat logistics. The moment the system stops, the moment it waits, it starts to lose the very quality it was engineered to protect. In these fragile hours, shelf life evaporates invisibly, long before the product ever reaches a shelf. In cold chain logistics, the most critical variable isn't distance, it's time. Not just how much of it passes, but how precisely it's managed. Time behaves like a corrosive fluid, invisible, persistent, and capable of infiltrating every part of the process. If not engineered with precision, it erodes quality, shelf life, and economic value. Like a forage harvester with misaligned blades, poor timing in meat transport leads to uneven results. Delays during loading, thermal fluctuations at borders, and gaps in ventilation don't just slow the chain, they fragment it. Quality breaks down, not from failure of refrigeration alone, but from microsecond decisions that go unnoticed until it's too late. That's why innovation today focuses not just on equipment, but on orchestration. In Singapore, integrating AI route planning with blockchain-based customs shaved 11 hours off beef transit without increasing speed. Those hours translated into 4 extra days of shelf life. Not through urgency, but through synchronization. The lesson is simple, but powerful. The strongest cold chains aren't the fastest. They're the most consistent. They function like precision machines, absorbing shocks, repeating performance, and resisting entropy through design, not improvisation. Imagine the entire system as a mechanical loom. Each border, container, and corridor is a spindle, rotating in harmony. The meat, a fragile filament, must pass through them without tension or pause. If any part falls out of sync, the thread snaps. This is the invisible discipline behind the meat on a holiday table. A choreography of machines, humans, and data, engineered not just to move food, but to control time itself. If this journey made you see meat transport differently, check the pinned comment. There's something there you won't want to miss.